So this year, I want to get you guys. I didn't do this last year. I guess before I dive into this, let me again reiterate my, or maybe expand upon some of the philosophy that I've conveyed to you. This class is a class in progress, right? This is the second year I've taught it, and I'm revamping at least 50% of the class, probably more than that. And one of the ways I'd like to do that is by having the students help me with that, help me tell me what they think is working, what they think isn't working. I understand that we have slightly different motivations, and sometimes I'm going to ask you to do things that you may not be completely excited about, but I do want to get you enthusiastic and engaged. And part of having that engagement is getting you guys to have a little bit of skin in the game. Help me create the class, so to speak. Help me create the class. And that's what these podcasts are about, and I'm going to do that in the lab as well. And we'll do it here in lecture. We'll do it in a number of different ways, just as a process, as a team. I need your help to make the class really good. I want it after 3 or 4 years, 5 years maybe. I want it to be the best class on campus. I really want that. One of the things in the lab that I want to try is, science is a pretty big realm, and this is meant to be a survey class to help you understand science. And one of the things that I didn't do last year that I taught this, that I want to do now and see how it goes, and you can tell me your experience. Science is intrinsic to it is journaling. So making observations, recording those observations, and cataloging those recordings, and being able to go back through them and look for patterns and draw conclusions from those observations. So journaling is really important if you're an experimental scientist, keeping an accurate, clear log of what you did. If you're a natural scientist, meaning a person who goes out and is purely making observations on the natural world, though it's the body of observations across time that becomes useful, right? So you can see how what the ice on, ice off day is in a lake, for example, and how that shifts with time. You may, within the span of your lives, you guys, no one here is probably older than 22 or 20. Yeah, I would guess 22 is the oldest in the room. Within the span of your life, you may not really have been able to notice a difference in, say, you lived on a lake, the time that the lake froze and melt in the year. But if you were to compare that to the observations made by your grandmother, for example, she would say, yeah, absolutely, the lake freezes a month later than it used to, and it melts a month earlier than it used to with time, right? So, and that's a kind of a natural science where you're just making observations. So in this notebook, we're going to do both, right? We're going to do some experimental science, and we're going to do just some sort of observational recordings in the notebook. I want you to go and get yourself a notebook. It doesn't have to be flashy, but I haven't gone to the bookstore to look and see what they have, but I assume they have notebooks there. And you want to get one that is not spiral bound, where the leaves rip out. In general, you want, one of the things about science journaling is, the ethics of science precludes you doing something where you're editing your data, like selectively picking and choosing, cherry picking your data, or et cetera, right? So just like a typical standard procedure is to get, when you're using a hard copy notebook, is to get one that's bound. And you do it in hard copies, even in this digital world, because a hard copy can't be tampered with, right? It's what you wrote when you wrote it, and there it is. There's the record of it. can't be corrupted, etc., etc. Lined or unlined, it doesn't matter. I'm going to be asking you to make some drawings. I think it's a good exercise, actually, to be able to sketch a little bit. We'll be looking, trying to incorporate microscopes. So, please get a notebook. Not asking you to buy a whole lot of stuff for this class, but a notebook should be manageable. If it's not, come to me and I'll get you one. Listen to the Week 1 podcast on Moodle. There's two. There's one by Sander Katz, who is the sort of father of the modern fermentation movement. A pretty interesting guy. I've wanted to get him up here to visit. He's here in New England. Interesting individual. Has fermented basically everything that you could ferment, and has made a life out of it. But there's a little interview with him, and so you're listening to the content, but you're also listening to the style of the podcast, trying to get a sense of what a cool podcast sounds like. There's another one on there by Zane Fields, who took the class last time, so you can hear what another student, the kind of podcast that they made, right? I'm not holding it up as the prime example or a horrible example. I'm not bringing a value judgment to it. I'm just showing you what some of the people in the past have done. All right. So his content doesn't actually apply, especially to the week, but I want you to think about it more in terms of what he did and how he did it, that sort of thing. Okay. So those are there, and you'll find the link under podcasts in the Moodle. All right. So then for your podcasts, instead of, just reflecting on what happened, what we talked about in class last time, I'm still open to your input here if there seems to be some real consensus that you want to do a class theme. We can do that, but I sort of came to this rather than having individuals or the whole class. I think it's smart maybe to have team themes so that you're gonna form yourself into a team of 2 or 3 people that are going to be able to be the production support crew for each other, although you'll be working on your individual podcasts. But if you think you can have themes across your team, right? So maybe 2 or 3 of you want to put a series together about, like, you were excited about spices. Another person I hadn't heard from you, but you had an idea as well.
So like beyond.
Yeah, or like bugs. Yeah, sure. Cool. That's a great topic. How do you guys feel about team themes? Give me a show of hands for people who feel strongly about the class theme. Okay, so virtually no one. Give me a show of hands for people who feel strongly about, like, individual. They don't really like even the thought of a team theme. Okay, who likes the team theme idea? So that's what we're going to do. Okay. And so last year, I didn't put enough structure in around this, and so by the end of the semester, I was like bludgeoning students to get their work in. I left it to the altruism of the students to keep themselves on a timeline, and that was a mistake. So I'm going to rectify that this year. And this is the timeline I put together. It's a pretty fast timeline, and that's what I want to talk about now. Is here. This is the structure I put in, but if you want to adjust it, we can, and I'm open to that. I think it may be warranted. So by Friday in lab, I want to hear from each of the teams just briefly, and I'll meet with each of you for like 2 minutes or something like that, each of the teams. And you can tell me what your team is, who's on your team, what your theme is, and hopefully you can come up with a topic by Friday. If you can't, I'm not super concerned about your individual topic, but if you need the weekend to like sit down, clear your head, and actually do some work on the internet and think about what your topic is, that's fine. If you can get it to me by Friday, that's cool. Because then I was thinking that by Monday, I could get you to give me, just think about a timeline for how, like week by week, what you want to achieve, right? What do you want to do this week in the project? What do you want to do the next week? And the reason I think it's a smart thing to do that is because this is how real projects work in anything, but certainly in science, right? You have some time window that you need to have like a grant review due. You've done some research, or you're going to do some research. You have funding, and you need to achieve X, Y, and Z by A, B, and C dates, right? So not just saying, okay, I'm just going to work until it's done. That doesn't make sense. Like setting like realistic production goals for yourself and trying, breaking the project down into really small bites and mapping it onto a calendar so that you can keep yourself on track, so you're not procrastinating, that you're sticking with it. You haven't lost the thread because you've taken 2 weeks off, 3 weeks off of even thinking about it. So I was thinking that you could maybe do that this weekend and give me that timeline by Monday. All right, so that's right around the corner here. And then I'm leaving all of that time in between sort of blank. That's what you're filling in. And I put an endpoint for you here. I thought final production draft audio recordings due by the 11th, so essentially a month from today. And you'll have to write, so there'll be your recording, and then there will be a little bit of a blog post that you will use to introduce it. If you've ever gone to a blog or a podcast's webpage, there's usually some kind of, intro or something, pictures or not, whatever. And then I'll have you guys get it embedded by the 15th of March. And then I'm going to have you give some peer feedback on each other. I'm going to assign, you won't have to listen to everyone else's in the class, but I'm going to assign you a few others in the class so that you can listen to that and give them some constructive feedback. I'm probably going to embed a date, like a draft feedback in there as well, too. I haven't really figured that out yet. But yes, sir.
So then after we get the...
No, so this is, there's going to be 2 peer feedbacks. And I haven't put the previous one that you're going to use to be able to make revisions. That's in this, what I have as tentatively 3 weeks there. And then the last peer feedback will be feedback that I'm using to consider how I assign a grade to your paper. So I'll listen to it, and like half of my grade will be that, but the other half I'll sort of take into consideration the feedback that is submitted by your peers, if that makes some sense, so that it's like a group assessment of how we're doing. Does that make sense? Okay. But there definitely will be some peer feedback in that realm over there, and I'll have to. That's a date I'll have to set for that, or at least provide you partners who will do that, and you can work it into your own timeline. Is this reasonable? Is the question I put to you guys now? Is this timeline, when you look at that timeline? So you have your everything embedded in the class blog by the 15th. That's a month from now. Is that something that you think that's enough time, or is it not enough time? Is it hard for you to wrap your head around that? Okay. All right. Well, I submitted this timeline to Tim Stonecipher to ask him what he thought of this. This is certainly faster than I did it last year. I'm trying to clear time at the end of the schedule, end of the semester, so you can have some time to not have this in your head and you can think more about the arsenic project. Didn't want those to overlap too much. This would have it done before spring break is what this would be. That would be right before spring break. So if you don't mind it going over spring break and going into the second half of the semester, that's okay with me too. Who feels like that might be wiser? You're sort of flickering. A couple half of you. Who thinks that this is maybe reasonable? Sort of. So it's kind of split. All right. Yeah.
Can you push it a week and still have it?
Yeah.
There, the 20th.
So let me see here. Looks like the midterm is on the 22nd. Oh, yeah, okay. Yeah, I guess we could push it a week, right? So I can push these dates up by a week. Yeah, the reason I was doing that, is that last week I didn't want you to be thinking about this. I wanted you to just be thinking about the midterm. I was trying to give you some room for that, So I would hesitate to move it up just a week. I would feel like it would be smarter to move it to the other side of midterm then. And then if that's the case, put it a week on the other side of midterms, spring break, so you can actually be on spring break and not be thinking about some project. Does that make sense? Yeah. Okay. Well, let's do that. I'll adjust those dates to make it like that. I'm just trying to strategize for you guys. All right. And we can adjust that as we get there too. See how everybody. If you're good at sticking to your timeline, then we'll be all right. But if like the majority of the class is not getting the production where they want, then we can adjust it as we need to. All right. So that's that. Any other thoughts? Okay. So I say the one thing you can do is start, even if you only have a vague idea of what you want to do, start recording some footage now. You can just record it on your phone, right? Maybe it's because sometimes that's interesting to listen back to, and maybe you get a little clip out of some recording of you're in your dorm room and you're thinking about something that's related to this. You're reflecting. I don't know how many of you reflect in the day, but you're reflecting and you do it and record that. Sometimes those reflections, you can embed them and then narrate around those reflections and weave a story together. Because sometimes in a podcast it can be the story of how you came to understand something or your exploration of an idea. Right? There's different ways of storytelling, and the more raw material you have, sometimes a form that you didn't anticipate can emerge from that. I found that to be the case. Or you're somewhere, maybe you go to the farmer's market downtown, which is every Thursday, by the way, like 2 till 5, I think, 5 or 6 downtown, at the Chase Commons in the building. You interview one of those people, or you just record the sounds you have your phone on and you're just recording the ambient sounds of the farmer's market. You can use that as background or texture in your podcast to make it sound more interesting, Or maybe you're in the dining hall and you record ambient sounds, or the kitchen, or whatever, that kind of stuff. So Tim wanted me, so this phone recordings bullet point here actually has 2 purposes. He wanted me to tell you that if you want to do phone interviews sometimes, there's a lot of cool people in the world, and say you want to interview one of them, but they live in whatever, California or something like that. You get them to agree to do a phone interview. The recording studio up in Lovejoy is the place for that. They have like a good setup to be able to do phone recordings, phone interviews, and make it sound not lo-fi and shitty. So if you want that, if you're going to do that, go either contact Tim or go up there. There's some other woman that is in that space up there can also help you with that. Yep. All right. And get a portable in Miller if you want. Figure out how it works. Okay. Are there any other questions? Yeah. You had... No.
Oh, no.
Okay. Yeah, cool. Stretch it out. All right. Was the lecture last time, I know it was a little bit dry because I'm just going over background. And this is new this year. I didn't give the background last time. And some students felt like, oh man, you put these chemical structures up there and I didn't know what I was looking at. I don't want that. Was it useful at all? So
It will be.
Okay, good. Yeah. I'm gonna continue with it, even though I'm getting a little off my timetable. But molecules is what I'm going to talk about today, and how to form molecules. So here are an example of some basic chemical formulas. H2O. I think everyone in here is probably familiar with that chemical formula. That's water, the chemical formula of water. And that, when you see H2O, without knowing anything about the connectivity of atoms, that could be H connected to an H connected to an O, or it could be three atoms in a circle connected like a triangle, or it could be HOH. And it turns out that that's what it is. It's a central oxygen with two hydrogens attached to it. And oxygen, I don't want to get too deep into explaining the orbital dynamics that are the rationale for this bonding. Hey, David. But take it as a point of faith that oxygen is able to form two bonds, and by sharing two covalent bonds, by sharing electrons, in this case with hydrogen, and it's also going to have two extra pairs of electrons. So electrons themselves like to run in pairs, right? There's going to be, the way electrons work is there's going to be one that has a spin in one direction, and they can occupy the same space, if you can bend your mind around that, as another one that's spinning in the opposite direction, right? So there's like spin up and spin down. Electrons travel in pairs, and that can be either bonding or non-bonding pairs. Oxygen has two bonding pairs of electrons in its valence shell and two non-bonding pairs of electrons in its valence shell. This sodium carbonate that we see below it, this is an example of a molecule that has both covalent or shared electrons and what's called an ionic bond. This is what we would call this an organic salt. But we'll see what ionic bonds, how that works in a bit. Covalent bonds are shared electrons, and ionic bonds are donated electrons, where one atom is going to just physically take the electron from the other atom. Like take the electron from the other atom, and the two atoms are going to become formally charged, where the one that lost an electron is going to be positive, because now it has one more proton than it actually has electrons in its shells. And the one that stole an electron is going to be negatively charged because it has one more electron than protons in its shell. And that opposites attract in the molecular world, and so those opposite charges will be drawn together. All right, so that's an ionic bond. All right, so then just a little bit of convention. This is, you'll see these molecules, and sometimes they'll be colorized, right? You'll see like this thing over here on the right, glucosamine. Glucosamine, really a good nutrient that is found, particularly in cartilage. So like when you boil bone broth, you make bone broth, you take a bone and boil the piss out of it. There's a lot of glucosamine in there, or in like really fine fish bones, like in anchovies or sardines or something like that, which are semi-cartilaginous. This glucosamine, this sugar, is in there, and it's great for your cartilage. It's an important nutrient. So I could put a picture of glucosamine up and talk about it, and when you are looking at that, You could say, well, what are all these different colors, and like, what does that even mean? There is a sort of a conventional color scheme that has been adopted. When you look at these molecules in general, carbon is depicted as being either black or gray, and oxygen is depicted as red. Hydrogen is often depicted as white, and nitrogen is often depicted as blue. All right, so as much as I can, I'll stick to that color scheme when I'm going to show you a molecule. That's not to say that actual nitrogen is blue or oxygen is red, and any of that kind of stuff. It's totally imaginary. But all right, just so you know what you're looking at. All right, so a chemical bond itself. This happens when two atoms are attracted by one way or another enough to each other to stay together. And I have already said that a covalent bond is when electrons are shared between two atoms. So let's break that word down. These atoms are covalent. They're valent electrons, the electrons in their valence shell, the outer shell, the electrons that are going to dictate how atoms interact chemically, they are shared, right? So they have a covalency with a pair of electrons, or maybe multiple pairs. They may have 2 bonds or 3 bonds. So atoms of the same element are going to form nonpolar covalent bonds. So like hydrogen gas or fluorine gas. I have fluorine over here on the right-hand side. Fluorine, an atom of fluorine can covalently bond to another atom of fluorine, and those electrons are being shared between them. And one fluorine isn't pulling on the electrons stronger than the other. Whereas if the atoms are non-identical, so they're 2 different elements that are covalently bond, this is going to be a polar covalent bond of some sort. And one of the atoms will just inherently, because of its a whole host of factors that we don't need to go into, but because it's different, it will be pulling on the electrons a little bit more strongly, and this causes a slight polarity in that bond, meaning that one of the atoms is going to be a little bit electron deficient because it had its electrons pulled away from it, and the other is going to be electron rich because it has pulled the electrons slightly towards it. This is not ionic; they are still shared, but there is a slight polarity. Yes.
Is that like when shared electrons at the bigger atom?
Yeah. It doesn't have to be bigger. It's related to a number of factors. Again, I don't want to get into shielding and all kinds of stuff, but at the base of it, all that kind of gets wrapped up into what's called electronegativity, which is a property of an atom that is just a measure of how strongly it pulls on electrons. And in general, the trend is electronegativity goes up as you head to the right on the periodic table and as you go from the bottom to the top. So fluorine is the most electronegative atom. And then it decreases towards electropositivity in the other end of the periodic table. What was I going to say? So this polar covalency is important because I'm going to talk about water, and it's good to understand water so we can understand some of the biomolecules and the biochemicals that are in food and what they do and how they work. So, all right. Talked about polar covalency. Well, this is like the poster child of polar covalency here is water. Water is a covalently bonded molecule. You see, so oxygen wants to satisfy what's called the octet rule, have 8 electrons, and it only has 6 in its valence shell. It wants to pick up 2 so it can form 2 bonds with hydrogen. And you see that picture in pink and purple in the right-hand corner there that shows each of those hydrogen atoms covalently bonded to the oxygen with 2 lone pairs of electrons sticking out. So we have 2 pairs of bonding electrons, 2 pairs of non-bonding electrons in water. So this gives water a pretty unique structure. it is this sort of tetrahedral structure with two bonds coming out and then two electron pairs coming out. It makes it sort of tetrahedral, but just considering atomic centers and the bonds along them, we call it bent. It is it's all three in a plane, and it's the sort of bent structure. So the hydrogen-oxygen bond is a polar covalent bond. Oxygen is more electronegative than hydrogen, so it's going to pull electron density towards it, and on top of it, and the hydrogens are going to be a little bit have a little bit of a positive charge. This funny little circle with a squiggle tail and a plus or a minus, that is a lowercase delta, and it's just meant to indicate a small charge, a little charge, not a big one, but just a little bit of a charge. All right. So this charge, these small delta charges, can cause an attraction, a hydrogen bond attraction between the negative and the positive ends of two adjacent water molecules. This bonding is transient and weak. It's a hydrogen bond. It will form and then it will break as two water molecules will kind of get attracted, and they're a little sticky, but then they'll come apart. It's sort of like two magnets. The atoms and the magnet are, the magnet is stuck together. You're not tearing that apart, but then two magnets, you can stick them together, and then you can pull them apart, right? It's a little bit like that. Okay. Any questions here? Can I move on? All right. And then the last concept is that in terms of covalency is the number of bonds that atoms can form. You can have single bonds. So for example, hydrogen, because of its electronic structure, it's in that first row, it can only form one bond. You don't have two bonds to hydrogen. You can only have one bond to any hydrogen atom. Oxygen, because of where it is on the periodic table, it can form two bonds. And those two bonds can be to two different partners or to a single partner. If it's to a single partner, that is considered to be a double bond. All right. Oxygen also has, like I said, those lone pair electrons. All right. So now let's think about carbon. Carbon can form four bonds. Carbon forms four bonds. Whenever you see an atom of carbon somewhere, it's going to have four bonds to it. All right? It's going to have four bonds to it. And that all four of those bonds can be single bonds, and if they are, they're going to be that the structure around that carbon is going to be tetrahedral, like you see on the left there. All single bonds are freely rotatable, always. Whenever you have a single bond, you can rotate around it. And I should have brought my molecular models in for this. I didn't. But carbon can also form double bonds. And if that's the case, the structure around the carbon is called triagonal planar. All four of those, the carbon and the three R groups, are all in plane. And the double bond, you can't rotate around it. It's like locks that geometry in around that bond. And that'll be important when we talk about fats. So for example, trans fats are saturated and unsaturated fats. This concept of double bond will be important. And then triple bonds. A carbon can form a triple bond. It's pretty rare to see that in biological contexts. It's a very high energy bond. It's very unstable. So the most familiar carbon triple bond that you're going to run into is acetylene, and they use that for blowtorches, right? So it's very hot, chemically energy dense molecule to form, because you're jamming all of those electrons into the same space. And electrons, I said opposites attract. Well, like repels like. Electrons don't really want to be near one another. which is why single bonds are tetrahedral. That's the structure that puts those bonds furthest away from one another in space. Does that make sense? Like if you made a balloon animal around carbon, you'd have the four in a tetrahedral shape. But if you were trying to make a balloon animal that had 3 legs going from here to there, you'd have to really work to bend those balloons into shape. Is that sinking in? Let's not worry about the triple bonds because they're not in biological systems that much. Okay. So, and then lastly is nitrogen. I'm just covering the big elements here in biological systems. Nitrogen can form 3 bonds typically if the nitrogen is not charged, but because of nitrogen's electronic structure, where it is on the periodic table, nitrogen doesn't mind being positively charged. And so very often you'll find a nitrogen that has 4 bonds around it. Okay, and that nitrogen is going to be positively charged because you can see here in the 2 on the right, 2 structures on the right, it has 3 bonds around it and that lone pair. That lone pair can actually, the nitrogen's not really holding on to that lone pair very well. And so some other atom can come and take one of those and form a covalent bond with them. All right, nitrogen. Any questions on that? Single, double, triple bonds? Yes. Yeah, the PowerPoint is on the Moodle. They're always on Moodle. They have been on Moodle. This has been on Moodle since the beginning. This slide because I may have switched it. So the first version that I had posted had this. The newer version may not have this. I don't remember. And then I changed my mind and decided to put it back. So whatever. I'll double check that. But yes, this is always all on Moodle. Ahead of class. Like I said, you can look at all these slides ahead of class. That's one way to, make the most out of class is look ahead, prepare ahead of time. All right, and the last of this stuff. So the covalency. You will often see, and this is the point. So this molecule I have on the left, they're like squiggle lines with an OH on the end. That's not like, some emoji or something like, oh, it's that represents this molecule that you see on the right with everything explicitly written in there. That would be called N-butanol. So when you're looking at this squiggle line with an OH, the lines represent bonds. The end of a line or a joint represents where a carbon is. And so if you were to look at this right here, this spot would be a carbon, and you're thinking to yourself, well, wait, I thought carbon only has to have 4 bonds. It does, but the bonds to hydrogen, we just don't include. So for example, that would be this carbon, these 2 hydrogens, we just exclude them for clarity. We just assume that any unaccounted for bonds to a carbon are going to be hydrogen. Any other hydrogens that aren't bonded to a carbon but are in the structure get written in explicitly. All right? So this thing that you see here is exactly the same as that. Does everybody follow that? Okay. This is important to me just because more than a lot of the other stuff I've already talked about, I'm going to be putting chemical structures, some, on the board, and I want you to be able to know what you're looking at, understand what it is that I'm showing you. Does everybody feel okay about that? David, yeah.
You said that spot.
Except the one that ends at the oxygen, that oxygen is the end of that line. Does that make sense? Was that your question? Yeah, okay. Yeah, if the line ends at some explicitly written letter, then that is the end of that line. Okay? On to ionic bonds. So ionic bonds are simply electron donation. Rather than being shared, the electron is being taken from one and given to another. So here's table salt, sodium chloride. When sodium metal, the sodium has a single electron in its valence shell and is super explosive. Did any of you guys have cool high school chemistry teachers? No? It's kind of dangerous. You take a chunk of sodium,
Throw it into the water.
you whip it into the lake, and it blows up. Yeah, it blows up because it's so super reactive. Yeah, it's really
How
reactive.
big is the
You can Google that. It's on YouTube. Pretty big. Yeah, what's up? No, you can't. And so I'm going to get to that. Chlorine, elemental chlorine gas, it is super poisonous. It's super toxic. It's caustic. And so sodium metal is explosive, and chlorine gas is toxic and will kill you like that. So for example, they use it to chlorinate water. You had a question? No, just sighing, thinking about the tragedy I'm about to describe, where they chlorinate water with this in some municipal water systems, and they're down in, I think it was West Virginia. One of the municipal water district was actually on a hill, and it's normally you're not supposed to do that. You put these in valleys. The tank of chlorine ruptured there, and all this chlorine gas it's heavier than air, normal air, and it ran down the mountain and just like killed everything in its wake. It just killed all these animals in this forest and got into the town. It was a bad story. It was maybe in the 90s, something like that. So how come sodium chloride is so yummy? We eat it all the time, every meal. Our body needs it. It's because the sodium metal with that extra electron is super reactive and chemically very different than when it donates its electron and gives up its electron. All right, it then becomes the sodium cation, positively charged, and we colored it in green there. And then chlorine becomes the chloride ion. It picks up an electron, and because of the electronic structure, it's now different, electronic structure. Its chemical properties are totally different than if it were chlorine gas. All right? And you can see in the sodium, the valence shell in sodium is actually, the previous one is completely clear of electrons, and so the new valence shell is the shell lower down. It's totally full, and it's happy. And chlorine just filled up its valence shell by picking up an electron from sodium. They have equal and opposite charges. They like each other, stick together. Is that making sense? This is what salt is. That's a salt. And so then it forms these three-dimensional, for table salt, the crystal lattice is a cube. It's just a very basic cubic structure. Different ionic compounds are going to stack together in different types of regular three-dimensional arrays. This is why crystals have so many different shapes depending upon the molecular structure of what it is you're crystallizing. Sodium chloride is very simple and just stacks very easily as a cube. All right. So if you were to take a salt crystal and look at it under the microscope, that's what it may look like. Maybe we'll do that in class. That might be fun. Okay. So yeah, just to remind you, this is a food class. Food has salt on it. All right. And then the next part is, well, how does this stuff go into solution? Like this, where the sodium and the chloride from this crystal get ripped apart from that crystal, and they get solvated. When we take salt and we stir it into water, the water molecules, I told you water was polar. Yeah, David. Oh yeah. When the water is polar, it has a positive end and a negative end to the molecule. The positive end of the water is able to aggregate around around chlorine and balance out the negative charge of the chlorine, and the negative end of the water is able to aggregate around sodium and balance that positive charge. So the sodium and the chlorine are now dispersed from one another. Their charges have been sort of balanced by the water, and it's called in solution. All right? Yeah, David.
Salt.
Oh yeah, brother. We're going to get there. Don't you worry about that. We're going to talk about taste for sure. Yep. The short answer is you just have salt receptors on your tongue. Yeah.
When they're separated in water,
They are ionic molecules. They are ions, right? They aren't. You wouldn't call them bonded together. It's not an ionic bond because they're in solution at this point. So the ionic bond has been broken. They have been solvated. Is the language that you would use. Their electrical structure has not changed, but they are now no longer a solid crystal. So, for example, salt has very high melting point temperature, right? You can take salt and you can chuck a bunch of salt in a pan and heat that pan up and just keep on heating it. And that salt's never going to go anywhere. Whereas if you take sugar, which looks the same as salt and also goes into solution, and you put that in a pan and you start heating the sugar, it's going to turn into caramel quite quickly, right? So the physical salt has a strong bond, but you put it in solution, and that ionic bond is broken up by the water that solvates it. Ariana. Mm-hmm. That's a great question. I should make a lab about that. That would be fun, wouldn't it? Yeah. So water boils faster with salt in it, and this is true because the salt, as you add the salt, so I told you that water can hydrogen bond with itself, and those hydrogen bonds are, we could have a whole lecture about water, but it's what gives water so many of its amazing properties. We take water for granted, but it's chemically really weird. Those hydrogen bonds, energy gets stored in those hydrogen bonds, right? And it makes the water, as you heat something up, you're adding thermal energy, and eventually a water molecule gets enough energy to tear itself away from the liquid and become a gas. Well, it has those hydrogen bonds to overcome it. And as you add salt, you're disrupting some of those hydrogen bonds. All right? So if you notice this, that water is losing degrees of freedom. It can't hydrogen bond with itself as much as it would like. It's stuck in with the salt there, right? And so you're changing the structure of the water by disrupting it with the salt, and you make it easier to boil. Yeah. No, cool.
might not be food, but hydrogen bonding between water molecules.
Yeah, absolutely. Yeah, okay, you guys know more than you let on. Yeah, absolutely. You guys got it. That's right. So surface tension. We'll talk about that later, though. We're out of time, I'm sad to say. We'll pick up on Friday.